Hello everyone. So today we will look at another technique which we commonly use to understand the construction materials. It is a thermal analysis, right. So in the next few lectures we will talk about the principles of various techniques which we use, and also we will see application of thermal analysis construction materials. Okay. So the first question comes to the mind: what is thermal analysis, right? So basically thermal analysis refers to a group of techniques which study the properties of materials as they change with the temperature. So the focus is on the temperature. As you are changing the temperature, how the properties are changing, right? For an example, any material, if you heat it up, the temperature goes up, right? But beyond a point, then there might be change in phase. Simple example, ice. For an example, ice will turn into water at 0 degree Celsius, and then that water will evaporate at 100 degree Celsius, right. Another example could be what happens when you like coal. If you burn coal, it will be gases coming out of coal, like inflammable gases, right. So depending on the material, you will see a particular response, right, and that is very unique to a particular material, how it responds to a change in temperature. So that is the focus of this technique, right. So thermal analysis is performed to obtain properties, right, such as enthalpy, thermal capacity, mass changes, and the coefficient of heat expansion, right. So just to keep in mind that whenever we change the temperature, something happens to the material. If we can capture that, it will help us identify a lot of properties, right, behavior of materials. So a lot of techniques come under this thermal analysis, right. We call it thermal methods. So and they are used for different purposes, right. It is good to know why we are using a particular technique. For an example, differential thermal analysis, DTA, as it abbreviated as DTA, used for understanding phase changes, reactions, lot of reactions, right. And what we are doing in this technique is we are measuring the temperature difference, differential thermal analysis. Anyway, we will go over each technique, but here I am trying to give you an overview. What are the different techniques, what property do we measure, and where it is used, right. Next is differential scanning calorimetry, DSC, where we are measuring power difference or heat flow, right, the differential thermal power. You can see it can be used to calculate the heat capacity. Also it can be used to understand the phase changes and various reactions. Next one is thermogravimetric, right, TZ or TGA, where we look at various reactions like where decomposition happens, dehydration, dehydroxylation, oxidation, etc., right. In this technique we measure the change in mass, okay, that is the property we measure in TG. There are a couple of others like thermomechanical analysis, TMA, where we measure deformations. It is used to understand mechanical changes, right, like and expansion. Dynamic mechanical analysis, DMA, is used for measuring moduli. It can be used for polymer to determine the polymer composition, glass transitions, phase changes. These are few applications, okay. So but in this course we will focus on DTA, DSC and TGA, which are commonly used in construction materials. So starting with the differential thermal analysis, right. First you need to look at the name, differential thermal analysis. Differential is term difference emphasizes an important feature of the technique, okay. Basically what we are doing, we are measuring the temperature difference between sample and reference. You have a reference along with your sample, and as you are heating your sample and reference together, you measure the difference, temperature difference, that is the key. So, you can see sample and reference are in the same cell, right, and you have a thermocouples to measure the temperatures, and finally we measure the temperature difference. Okay. So, delta T equals to Ts minus Tr, that is the key, that is what we are measuring. So, what is the principle, measurement principle behind DTA? Now, we said that we are measuring the temperature difference. So, basically if you look at now, let us focus on the left plot. What we are doing here, we have plotted temperature versus time, right. So, you have a furnace, for an example, you have a sample and reference. Now, you are heating both together. So, first look at the furnace temperature. So, we have programmed our heating rate such a way that it increases linearly. So, you see that solid line shows you how the furnace is heating up, right. Now, the reference, you have to make sure you use the reference which is not reactive, right. So, that is one of the key features. I have mentioned here alumina, basically alumina, silica, silicon carbide are commonly used reference materials because they do not change with the temperature in the range we are interested in, right. So, you see some lag here, but more or less the reference temperature also is increasing in the same rate, clear. You have this dotted one for reference, right. You can look at the legend also. Now, what happens to the sample, that is where we are more interested in, right. So, I will just go over a couple of things, but then we will go in detail. So, when something melts, right. So, suppose the sample temperature is also increasing, right. When the melting starts, then what happens? The temperature does not increase, right. Something is melting, so it will melt, right. So, you see there is a flat line here. So, that means temperature is constant, right, because it is a melting, right. But once the melting is over, then you see there is an increase in temperature, right, clear. Then it comes to next regime. So, now if you look at it, now if we plot the temperature difference, what we are doing here, as we said, in differential thermal analysis, we are plotting temperature difference with time. So, this is the time axis. So, what you see in melting is difference, means we are looking at this difference, this is the difference here, right, difference between reference and sample, right. So, when something is melting, you see the difference is increasing, right. So, this thing we are plotting it this way here, right. Once the melting is completed, now you see the difference has decreased, right. So, this also tells us that it is an endothermic phenomenon. Endothermic means melting will need heat, right. You are supplying, like you are heating it up, so that heat is being used to melt the material, right. So, endothermic peak tells you that something is melting. Depending on the reaction, now further if you increase the temperature, right. So, now you are here, in this case you see something different, the temperature is decreasing. When that will happen? Right, it depends on the temperature where you are. Exothermic means then you will release heat. When you release heat, then the temperature difference will reduce, right. It depends on the reaction, the material, what happens as you heat it up. So, in this case you see this exothermic peak. Exothermic reaction will lead to increase in temperature of sample. So, your difference with reference will reduce, right. So, these are some signatures, like in a DTA curve you see these kind of things, right. You will see endothermic peaks, you will see exothermic peaks. So, that will tell you what kind of reaction may take place, right. So, also important to keep in mind the reference material which is used in DTA analysis, DTA should not react, right. It's so alumina is commonly used reference material to analyze cements, for an example, right. Silicon carbide is another material, right. But as you know, we have to use a material reference material which does not change with temperature. Okay. Now, we talked about, we are interested in measuring temperature, right. So, it is also good, it is important to understand the principle of thermocouples. Thermocouples are used to measure the temperature, and there is something involved in that, right. It is not very easy to measure temperature, we are talking about 1000, 1500, 1600, 1700 degrees Celsius, right. What do you use? What kind of thermocouple? So, we will just go over some basics. So, basically it relies on a principle that when you join two dissimilar metals for an example, and now if there is a temperature difference, that will lead to current, thermoelectric current, and by measuring that voltage we are able to measure the temperature. So, see, thermocouple is an electric device consisting of two dissimilar electrical conductors, right, forming this electric junctions at different temperatures, right. So, you have two different materials, that is very important, and if there is a temperature difference, that will lead to this electromotive force, EMF or voltage. Once you measure the voltage, we can get an idea about the temperature, right. So, thermocouple produces a temperature dependent voltage as a result of thermoelectric effect, right. So, based on the temperature difference, you will get the different voltage, and that can be calibrated. So, depending on the type of materials you have in a particular thermocouple, you can calibrate it. You can calibrate it means you can calibrate like this, here you have a voltage plotted against temperature for different types of thermocouples, right. So, you can calibrate it. So, you know at what temperature you get what voltage. So, if you know that voltage, you can easily calculate the temperature. This is the characteristic function, okay. And as you see here, voltage can be interpreted to measure temperature. That is what we are doing in thermocouple. So, we are measuring the voltage, like measuring, and then using that voltage to calculate the temperature, right. So, this voltage basically depends on there is a relation here, you see voltage depends on the temperature difference obviously, and also Seebeck coefficient. So, Seebeck was the scientist which proposed this theory, Seebeck effect, right. You can go and read about it, but here just briefly just wanted to show you that there is a dependence between voltage and temperature depending on the material. So, you see also here is a table where you have different types of thermocouples, type B, type E, type J, K, N, R, S, T, and see notice the conductor combination, it depends what kind of material you are using. In type B you have a platinum 30% rhodium and platinum 6% rhodium, okay. These are the two dissimilar metals we are using, okay, or electric conductor in a sense. Also, let us look at the BRS for an example. BRS are commonly used for high temperature measurement. You see what is the temperature range used for BRS, type BRS, you are talking about 1370 to 1700 degrees Celsius, for B 870 to 1450 degrees Celsius, quite high. So, this is the temperature range used if you are want to use these types. So, it depends on your requirement, what kind of temperatures you want to measure. If you want to measure low temperatures, then you can use like type E, J, right, for an example, right. So, it is very important. So, that is the principle of thermocouple, that is what we are measuring in DTA, right. And here you can also look at these we use. So, for an example, type J is made of iron and constantan. What is constantan? Is 58% copper, 42% nickel, right. It gives you composition also. Basically, we are talking about two dissimilar electric conductors, right. Okay. So, now let us look at what kind of processes or phenomena can cause this temperature change, right. We want to study a process, so we want to know like what kind of processes can be studied using this technique. As long as there is a heat release or heat absorption, right. For an example, adsorption, we look at the physical properties. So, something is getting adsorbed, right. It is typically exothermic reaction. It involves release of heat. So we can measure it. Desorption, it is a endothermic, right. Crystal structure change, when crystal structure changes, typical crystallization, melting, vaporization, sublimation, these are the examples of physical processes, right. Similarly, you may have oxidation, right, what we typically see when you expose materials to oxygen, right, environment, oxygen rich environment, you will have oxidation. Reduction, breakdown reaction. Chemisorption. Chemisorption is different than adsorption in a sense that you have now chemical bonds. Adsorption is not that strong. Adsorption, you do not have chemical bonds. Here you have some chemical bonds. Solid state reactions. These are some physical and chemical processes where you have some temperature, heat temperature change. Now let us look at the factors which influence DTA curve, right. Now we know, okay, so we know how to measure the temperature using thermocouples, different processes. So we get a typical curve. Now it is important what are the factors which can influence your DTA curve, right. If you carry out an experiment, it is important to look at that. So there are a lot of instrument factors, obviously, like furnace atmosphere, right. What kind of atmosphere you have in the furnace, right. Suppose you have oxygen, then you may trigger oxidation. If you have a carbon dioxide, you may have carbonation, right. So furnace and atmosphere, furnace size and shape, sample holder material and geometry, heating rate, thermocouple location in sample, these are some instrument factors which can affect your DTA curve. Also there are sample characteristics. What kind of sample, like what is the particle size, right. If you are looking at the powder, what is the particle size and how it influences your DTA curve, right, that is also important. Thermal conductivity, heat capacity, packing density, how well you have packed your powder, right, for an example. Sample amount, 5 milligram versus 10 milligram versus 15 milligram, 20 milligram, right. These are some sample characteristics which will influence your DTA curve, degree of crystallinity. So same thing, now we will go over. So heating rate, for an example, we said like heating rate, right, you are heating the material like sample. Now I can use 5 degrees Celsius per minute versus 10 degrees Celsius per minute versus 15 degrees Celsius per minute. I am heating the sample, but is it going to change, right? That is what we are focusing. So heating rate means, higher heating rate means broader and deeper peaks. We saw that in DTA you get the peaks, right? You may get endothermic peak, exothermic peak, right, depending on the change. So when you have this increase in the heating rate, means your peak will be broader and deeper, okay. I think there is one example after this. Sample mass, higher mass means broader and deeper peak. Similar effect is seen when you increase the sample mass, okay. Now particle size, how that affects your DTA curve. So everyone is familiar, when you have a smaller particles will tend to react faster rate, right, faster reaction with smaller particles, you have higher surface area, right. So leads to more delayed peaks with coarser particles. If you have coarser particles, will lead to more delayed peaks, okay. Also there is the additional distortion if the reference has a totally different particle size, because we are talking about the reference material also. If there is a very much difference between the particle size of a sample and reference, you will see some distortion in the peak, that is what it says. Particle packing, how it affects the DTA curve. See, dense packing implies higher thermal conductivity. If you are packing something densely, that means you have a higher thermal conductivity, right. Whereas loose packing implies more permeability, right. So higher thermal conductivity means might lead to quicker reaction, right. Thus the type of reaction is important. Furnace atmosphere could be important in some cases. For an example, in cement testing we usually use nitrogen purged atmosphere, because we do not want it to react with carbon dioxide, for an example, we do not want carbonation to happen. Also we do not want any change, so we use nitrogen rich environment. So these are some important factors you have to always pay attention when you do experiment or you look at the data in literature, right, because these things will change. So I will give you one example. So one of the most celebrated example of the application of DTA, right, to material science is this. Basically, it relates to the use of high alumina cement, which in some circumstances led to the weakening and in extreme cases the collapse of concrete structures. So, high alumina cement was being used some 30-40 years ago. So, at the time there was some issue with that, right. People noticed that it was weakening the structures, also in some cases was leading to collapse. So, wanted to know why, particularly with the high alumina cement, right. The problem actually arose because of the conversion. Add water to your calcium aluminate cement, you form this calcium aluminum hydrate CaH10, and it gets converted to C3AS6 and AS3. Okay. So, this conversion, right, it leads to loss of strength. Okay. We want to know what is the extent of conversion, right. So, in this example, obviously if you look at the DTA, right, this is the now typical DTA curve for calcium aluminate cement, right. So, you see this peak, one peak, then this peak, right, this is the DTA curve. So, first peak is because of the dehydration of CaH10, right. You know, this is the reaction, right. You are forming now these two phases C3AS6 and AS3. I am using cement chemistry notation. AS3 is, you know, it is written as Al2O3 3H2O. A means Al2O3, H means H2O, C means calcium oxide, C means, okay. So, now the second peak is due to dehydration of AS3. This peak is third one is because of the dehydration of C3AS6. This is the temperature axis. Notice x axis is your temperature, right. Now, if you have to get the extent of conversion, simple thing would be you can do y over x plus y, like if you know, right. This is obviously not exact because we are now looking at the peak height. Usually peak height is used when there is quite a bit of overlap between the peaks, right. Then it gives you some approximate reasonable value, but just wanted to show you that way they were able to quantify like what is the extent of conversion. So, applications of DTA are sample identification, because you can identify samples, it will have its signature, you know, where you are seeing this dehydration for an example, right, because that is dependent on the phase you have, right, it has particular signature. Quantitative analysis. So, area under the peak is the representative of mass of phase in sample, right. Also extent of reaction, any extent, you know, what is the degree of reaction we can calculate. Okay. These are few applications of DTA. Okay.